For graduate students, I'm pretty sure you have seen my email. Make sure to go on Blackboard, introduce yourself if you haven't already, to find your partners for the project. You can actually mix and match. So what I mean by that is that online students can group team up with face-to-face students, and so on and so forth. And undergraduate students, if you are interested in doing the project, you are welcome to do so. Yeah, actually, if you can think of a project that you want to work on for undergraduate students, and if I see the project is comprehensive enough, I can actually drop the exam, one of the exams or all of the exams for you, and ask you to only work on the project. So think of it as an incentive to get you to work on a project. Is this clear? Okay, let me just make sure we are recording. Hopefully the online students can hear me clearly. Yeah. So what was the last thing we talked about on Monday? We talked about the surface tension and viscosity, right? The dependence of viscosity on temperature. So let's talk about aerodynamic forces. Before moving on, if you recall, I told you that the material I'm going to cover for the class is subject to change. I had to talk to Dr. Farooq, who is the graduate director of the department. He actually recommended doing fluid mechanics for the second part of the class instead of the compressible fluid flow and viscous fluid flow, because we have two separate courses that cover those topics, right? So we're going to do inviscid incompressible aerodynamics, which means the theory of airfoils, wings, whatever, low speed flight, and then we will move on to fluid mechanics, which is an easier topic compared to viscous fluid flow. Yeah, so I'm going to revise the course schedule on Blackboard. Is there any questions? No? Okay, so let's start with aerodynamic forces. The first thing you want to understand when it comes to aerodynamic forces is the nature of the aerodynamic forces, or what causes the forces, the reason behind the forces. Okay, to answer this question, you of course have to understand the reason any fluid exerts any force on a solid that is immersed in it. Right? Think of a sphere or a circle that is inside a pool of water, a flow of water is approaching it, right? We are going to have two types of force that the water is going to, two types of force per unit area actually, that the water is going to exert on the circle. The first one is the normal force, or this way, the normal pressure or normal stress, and the other one is the tangential force, which we talked about, tau. Okay. On any object immersed in some sort of fluid, right? We are going to have these two types of forces: normal forces, pressure forces, or shear forces, right? That are tangential to your body. When it comes to aerodynamics, we are always immersed in a fluid, then air, right? Air is a type of fluid, right? And think of a cross section of a wing, which we call airfoil in this course. The same thing is going to apply to airfoil as well. Guess I'm going to use this. We are going to have normal forces as well as tangential force on each point of this object, right? This two-dimensional object. And these are going to be the main mechanism behind the aerodynamic forces that are going to be exerted by air on this object, right? essentially, you have to take the integral of this pressure and tau, this P and tau, over the surface of this aerofoil. A two-dimensional cross-section of wing is called airfoil. We are going to discuss that later in detail, but just in case I use this a lot. If you don't know, here you are. In British English, they call it aerofoil. So there is an O here, something like that. But in the United States, we call it airfoil, right? Two-dimensional cross-section of the wing. So we are going to have a normal pressure distribution all over the wing, as long as it has air around it, and we are going to have a shear distribution all over the wing as well. If you take the integral of these forces, you're going to have the resultant force and moment that is being applied on this airfoil here, right? The goal today is going to find the relationships that those forces have with each other and with these two, pressure and temperature. Pressure and tau. Normal pressure and tau, okay? Let me actually write this down. So the reason we are going to have any aerodynamic forces is pressure distribution and shear distribution as well. Okay. Any questions so far? No. So this pressure and shear are a function of the location of the surface, right? The pressure and shear is going to be different here at this point at the leading edge than what it is on some random point on the upper surface of the wing. So to find the resultant force and moment, we have to have the distribution of this pressure and shear, which can be calculated using numerical methods or experimental methods inside the wind tunnel, or there are a lot of different methods that we can do to calculate them. So in this course, we usually think of this as given. These are the distribution over a wing, the pressure, normal pressure, and the shear stress distribution is given in the problems. So that's not going to be the goal of the course. But as I said, the presence of these two will cause a resultant force R and a moment. Okay. There are a couple of quantities that we have to become familiar with before moving on. The first one, and probably you have heard about these quantities before. I just want to review them. The first one is the velocity of the air downstream the object. In this case, it's an airfoil, right? This one is called the free stream velocity. Or whatever property you are going to assign to air, far away from the object is going to be free stream that property. Free stream pressure, free stream temperature, free stream whatever. And we are going to use the sign infinity for it. So V infinity, free stream velocity. Okay. Of course, wind or air can approach your airfoil at a direction, at an angle. The angle it makes with the chord is going to be the angle of attack, or alpha. And then the next thing we want to become familiar with is the projections of this resultant force. As you can see, this resultant force is at an angle compared to the wind or the chord of the airfoil. or the center line of the airfoil, right? So we can have two different approaches to the projections of the resultant force. The first one is going to be normal to the center line of the airfoil or the object for that matter, right? The normal projection, normal and tangential to that. Normal projection is going to be called the normal force. Tangential projection of that resultant R force is going to be called axial force, so N and A. But more famous than these normal and axial force are the forces that are normal and tangential to the direction of the flow. The force that is normal to the direction of the flow is called lift. That is responsible for lifting your aircraft, right? And the force that is tangential to the direction of airflow is called drag. Okay. Is there any questions? I'm pretty sure you have heard these names, but the lift and drag are pretty common in fluid mechanics analysis. And you actually should have had a chapter on, or some part of a chapter on drag calculations in your fluid mechanics, right? Yes? Okay. Yeah. So here, today, we are going to find the relationship between these two forces, these four forces with each other, and their relationship with the pressure distribution on the wing, on the airfoil, or on any object for that matter. Okay, let's actually find the relationship with each other first. So again, let me actually draw another picture. Here's the center line. We have N and A. And then let's say this is the direction of the flow. We are going to have lift and drag. So what is the angle these forces, lift and drag, make with normal and tangential and axial force? Any guesses? We have only introduced one angle so far, so that should be it, right? You don't even need to think about it, because we only have one angle. So angle of attack, right? The angle, if you just do some trick calculations or trick observation, visualization, whatever, the angle lift makes with your normal force is going to be alpha, and the angle your drag force makes with axial force is going to be the angle, the same as angle of attack as well. So based on this analysis, we can actually find a very easy, simple relationship between the two. Your lift, let's actually see. I use a lot of colors. We want to find lift and drag based on normal and axial force. Let's see if we can find the relationship together. How do you think these two are related to each other? We have the angle they make with each other, and we want to find the relationship, right? And no ideas whatsoever? It's just a mathematical calculation, right? So let's say we want to let's do lift, and then I'll ask you to do the drag yourself. So lift, we want to find the projection of this force on lift, right? What is the projection of this force on lift? N cosine of alpha, right? Yes? Okay, so we want to find the projection of a vector on another vector, right? So n cosine of that vector. We have the angle between the two, right? But what about the projection of this force, axial force on lift? Does this force have any projection, or can we have any component on lift? So what is the component? We have one, yes. It should be negative a sine of alpha. Why is this a negative sine of alpha? It's pretty simple, because the angle this makes with lift is actually 180 minus alpha, right? So actually the correct projection should be a cosine of 180 minus alpha, right? Or 90 minus alpha, sorry. Pi over 2 minus alpha. Or is it 180? Pi over 2 plus alpha. Let's do that, yeah. Okay, so cosine of, if you recall from your mathematics or calculus, cosine of pi over 2 plus alpha is equal to negative sine of alpha. Do you remember this? Or yes or no? Okay. How many yeses are there? 1, 2, 3, 4, 5. And you can lie. Okay, that's good. You're honest people. That's all right. I mean, we have the equation. You don't need to calculate it. So, based on this logic, what would be the relationship between drag and normal and axial force? Yeah, I need everyone's contribution to this, but I want to make sure we are all clear on the calculus of it. So I'm going to start from somewhere. Who's the unlucky person? Let's start from you. So what do you think? What do we need here? So we want to find the relationship between drag and axial and normal force, right? And based on this, we know that it is a cosine-sine relationship. Okay? So the first thing you want to do is to find the projections of these, or components these vectors make on this vector here, right? Okay, what do you think it should be?
Can you just rearrange it as well? So you start with a sine alpha and your n is sine alpha.
Okay, so a sine alpha. So what you're saying is that it should be a sine alpha and n cosine alpha. Okay? Minus. So let me ask you this. The idea was, that's the idea. You need to find the angle between the two vectors first, and then the component one vector makes on another one is actually the magnitude of that vector multiplied by the cosine of that angle. But you're telling me it should be a sine of alpha for drag. But the angle these two makes is alpha. Shouldn't it be a cosine of alpha based on that logic, right? So do we agree? Do we all agree? So a cosine alpha. Okay, what about the next part? Let's actually, I need a volunteer this time. I don't want to go over all of the class. Not you. Someone else. The volunteer for the other other component. Go ahead. Is it positive or negative? Positive, that's correct. Why is this positive? Because the angle that it actually goes back to the sine relationship again. The angle this makes this time is pi over 2 minus alpha, and cosine of pi over 2 minus alpha is equal to sine of alpha, right? Okay, so the angle the other time was pi over 2 plus alpha. This time is pi over 2 minus alpha. Okay, this angle here, this is pi over 2. This angle is going to be pi over 2 minus alpha. But for the other time, we had pi over 2 plus alpha. It's just a sine relation, right? So we have the first two aerodynamics equations that you are going to see in this course. And you are not going to use these equations that much because we don't really use the normal and actual force in the VL, like airfoil and wing calculations. But you have to understand them. Okay, so is there any questions here? No? Good. So let's continue. The next step is to find the relationship between, we already have the relationship between lift and drag and normal and axial force. We want to find the relationship between normal and axial force and the pressure and shear on the wing. The reason we don't do lift and drag as a function of pressure and shear directly is because over there, if we do lift as a function of pressure and shear, we are going to involve two angles. The first angle is the angle like the pressure makes with your cord. Let's call it theta, and then we have alpha. But since we already have this relationship, we can only use normal and axial force, and then they plug in the equations we're going to find for normal and axial force as a function of pressure and temperature here, right? So we don't need to deal with the trigonometry calculations twice, right? And we're going to deal with it twice, but we don't need to make it more complicated than it is. Does this make sense? Okay. So let's take a look at another airfoil. This time, let's take a look at this point, random point. We have pressure and shear. And then you have the core, the center line, your normal force, and your axial force. We want to find normal and axial force as a function of P and tau. That's the goal here. So the first thing you want to do is to find this angle. This angle, right? Well, let's actually do this. So the angle your pressure makes with the normal force is going to be called theta, and the angle tau makes with the normal force again, with the tangential force, axial force is going to be called theta. They're going to make the same angle, right? And this theta here depends on your curvature, the curvature of this airfoil. So this theta is a design parameter, right? This is not something you have to find. This should be given to you by the person who has designed the airfoil, right? As long as you have the curvature of this airfoil or like whatever the wing, the object, you should be able to find that theta. You should be able to integrate over that theta. Does this make sense? Okay. And we actually, the sign convention here is that, this sign should be this way. We are going to assume that theta is positive in the clockwise direction. that's just an assumption. It's going to change the negative and positive sign when it comes to your direction. So let's actually try finding this force. Let's try dealing with a wing, right? We want to find the force on this narrow band here. This is going to be normal. Again, since P and tau are a function of your location here, the first thing you want to do is to find this small element of force or the derivative of the force, right, dN or dA, and then you want to integrate it over the whole airfoil. Okay, let's do that. The first thing we assume is unit depth. We assume we're going to have unit depth here. And we also are going to assume that the pressure distribution over this small band of, we are going to call it ds, the dsu, because it's in the upper surface of the wing, and it's just the length of this small band. So the area of this small band is going to be ds multiplied by 1. And we have the angles. Right, dN, dA. Is this clear? So we have dN and dA, right, normal to your chord and axial to your chord. You have tau and P, normal or tangent and normal to the surface of the wing. Okay? And we essentially want to find the same relationship, the same relationship. So finding N or dN as a function of P and tau. So the first thing you want to do is to find the components that P and tau have on N, right? Does this make sense? It's essentially the same operation we did for lift and drag. Is it clear? Or no? No? Not clear? Yes? Okay. So, can you tell me what is the equation then? For normal source, this dN. Okay, let's do this. Okay, so you are in the correct path, but the answer is not correct, right? The first thing you want to look at is the direction of the P is different from the direction of the N, right? Compared to here. They were in the same general direction, right? But P here is actually in the opposite direction. So we need a negative sign here. Okay? That's the first thing. And then the next thing, let's take a look at the units. What is the unit of force? Newtons, right? What is the unit for or dimension for pressure? Or if Pascal, that's correct. But that essentially is newtons per meters squared, right? What about theta? Dimensionless. There is no dimension for angle, right? We use gradients are not dimension, are not the unit, right? So timeless. So this equation is actually a wrong equation. There is no equivalency between these two sides of this equation. This is in newtons, this is in newtons per meter square. Okay? That's something you have to be mindful of always. That's actually this is something that you are going to see a lot in the course, in your calculations. So we need another parameter on the right-hand side of the equation. Multiplied by the area. What is the area here? DSU multiplied by 1, right? The area of this band, this small band. Okay? Exactly. So DSU multiplied by 1, DSU multiplied by 1. Okay. That is going to be your force distribution. But what is going to happen to this equation in 2 dimensions? In 2 dimensions, we are essentially going to lose the depth, right? So we are going to only have ds here, and your force is going to be force per unit length, right? So newtons per meter. And we are going to use prime for it. And that is true for any force we are going to use in this course, right? If you're using lift, L prime refers to lift per unit length, right? D prime is going to refer to drag per unit length, right? If it was double prime, it means that it is a point force. It is essentially a pressure, right? It's going to be force per unit area. Does that make sense? Okay. So since we are only, at this point, we are dealing with 2-dimensional cases, we are going to stick to N prime. So let's do dA prime. Who volunteers for this one? Something that you have to keep in mind is that this is N prime for the upper surface. And we want to do the dA prime for the upper surface as well, right? We actually, yes, it does, right? But the idea was at the beginning, I assumed the depth of our wing is 1 meters, right? So I just removed the multiplication by 1, right? So essentially didn't change it. And whenever you are dealing with something per unit length, you are assuming your depth is 1, right? That's the hidden assumption. Okay. So, this one. Who wants to go for this one? Positive tau, okay. DSU, we are going to get the negative P sine theta DSU. Right? The reason behind the negative P's is because of the direction of the force, not because of the cosine and sine relationship. So, which is not the case for the negative sign and positive sign we see for the shear. Okay, so let's do the same analysis, the exact same analysis, this time for the lower surface, right? What do we have for the lower surface? We have P in the other direction, and then we have tau in the same direction. So the main difference between the lower and upper surface is the direction of pressure. So this time pressure is in the same direction as your normal force. So who wants to give me dN prime for the lower surface? Let's actually call all of these TU. That U refers to upper surface, low refers to lower surface. dn prime for the lower surface. Someone else. Thank you for your for you volunteering. You want to jump in? What's so hard about it? You have the other equation. The only difference between the two is the direction of the P, right? So I'm pretty sure you can guess what the equation is going to be. Just one sign though, right? Just a sign for P. Because the only thing that is really changing is the direction of the P, right? So we're gonna get positive PL cosine of theta. And keep in mind that these are multiplied by DSU, so make sure you have the correct equation. DSU minus tau lower sine of theta ds. This is DSL, right? DSL. Okay, so who's gonna tell me what will we have for dA prime on the lower surface? Son of T. That's it, exactly. Thank you. So we're gonna have tau L cosine theta DSL plus, this time plus, PL sine of theta DSL. Any questions so far? No? If you are confused about the sine and cosine relationships, please let me know, because we are not going to use these equations that much, but the sine and cosine relationships are going to come up later. So you have to make sure that you are up to speed on those. If you don't remember them, we can go over them right now, okay? You don't want to ask me questions about them during an exam, because it's not going to help you. I will explain to you during an exam, but it's not going to help that much. Okay, so let's continue. So we have the derivative of the force. We have the dn prime and the a prime, right? How can we find the total force? We essentially have the force that is being applied on a very small element of surface, right? A very small section, DSU. And we want to find the force over the whole thing. How should we do that? Take the integral over the surface, exactly. So that's something that we have to be mindful of, is that you have to take the integral over the upper surface once, then add the integral over the lower surface second time, mainly because we have two different equations for it too. Or you can add it into one integral as well, but we are going to separate the integral. So let's do this. Your n prime, force per unit length, is going to be integral of, let's do the upper surface first, the integral from the leading edge of the airfoil to the trailing edge of the airfoil. Right? Are we all clear where the leading edge and trailing edge are? Yes? Okay. So I can actually take the negative sign out here, out of the integral, Right? We have two negative signs. So negative integral of leading edge to trailing edge. Pu cosine theta dsu plus tau u sine theta dsu. This is the first part of the integral for n prime. Then you want to do the lower surface. So leading edge to trailing edge of PL cosine theta dsu minus tau u sine theta, that's PS, yeah, cosine. Tau u sine theta, that's dsl, sorry, dsl. It is clear? Okay, so let's do the A prime now. For A prime, you are going to get the integral from LE to TE, upper surface integral, tau u, cosine of theta, dsu, and then we have the negative sign for pressure, right? Sine of theta, dsu, plus the integral of leading edge to trailing edge, tau L cosine of theta dsl plus P sine of theta dsl. So you have these huge equations for n prime and A prime. Then to find the L prime and D prime, you have to plug these into the previous equations, the first ever equations we saw here, the relationship between lift and drag to find the lift and drag. Any questions about those? No? Okay. The next step is to find the moment. You can find the moment over any point on the surface or inside your object, right? We want to find the moment around the leading edge. So we want to find the moment around the leading edge. And we should talk about the sign convention when it comes to moments as well. Whenever you have a moment that is going to increase the angle of attack, if you will, or it is going to pitch off the airfoil, your moment is going to be positive. And whenever the moment is in the other direction, which means that it's going to pitch down, your moment is going to be negative, right? This signs is going to become important the second part of the class where we are talking about flight mechanics a little bit. So have to be clear about the sign. This is a sign convention, so we can of course reverse this convention and redo the whole equations, but you don't want to reinvent the wheel, right? People have used this for a long, long time, this convention. Okay. Again, let's say this is your arbitrary points on the upper surface. You have tau, you have P, and we want to find the moment these two forces are going to induce at the leading edge. Okay. The next thing you want to do is to set your coordinate system. We are going to put the coordinate system on the leading edge, right? To find the moment, the first thing we want to do, the next thing you want to find is the distance between the point you are calculating the moment for and the forces, right? We're going to call this distance x, and we're going to call this distance y. This. And then, if you change the perspective from P and tau to normal and actual force, you can find your moment pretty easily, right? What is the moment the normal force induces on the leading edge? It's the force multiplied by that distance, right? What is the force? And that distance is x here in this case. What is the moment the actual force induces on your leading edge? That distance multiplied by that distance here is y, by the force itself. You have the normal force and actual force. You want to calculate the moment. So essentially you have to multiply everything by a distance, but those distances must be included inside your integral. So it's not the integral multiply the thing. So I'm going to write down the final equations, the final integrals from my notes. I'm going to give you the upper surface moments. Do you see this color? Okay. So which, what about green? What about this? Okay, so dm prime upper surface is going to be integral of leading edge to trailing edge. Pu cosine of theta plus tau u sine of theta multiplied by x minus, that's actually plus x dsu, and then let me actually write it down here. I'm sorry, dm prime, there is no integral. So pu cosine of theta s dsu, yeah, plus negative pu sine theta tau u cosine theta y dsu. We can write the same thing for the lower surface. What do you think the difference will be between the upper surface and the lower surface equations? Based on the discussion we have had for the forces, right? We had a discussion of the difference between the upper surface force and lower surface force. Based on that discussion, I'm asking you, what do you think this will be? What do you think the difference between the upper surface moment and the lower surface moment will be? You have to speak up. The direction of pressure. You essentially you're going to get the same equation for the lower surface as well. The only difference is going to be the direction of pressure. So you're going to get negative PL cosine of theta plus tau L sine of theta x dsu, and plus positive PL sine of theta tau u cosine of theta y dsl. Does this make sense? Okay, and for the final moment calculation, you essentially have to take the integral of these two equations here, right? Just to add them up, take the integral. Does this make sense? Are we clear on what this derivative of moment on the lower surface would be? It's essentially exact same equation. The only difference is going to be negative pu cosine of theta plus whatever, positive p, negative pl cosine of theta, and then positive pl sine of theta. Okay, that's going to be the only difference. And then to calculate the final L, you only have to take the integral. Okay. So we have the final equations for the forces, for the moments. We can, of course, we can simplify things a little bit if you do some mathematical manipulations, which is a thing we are going to do in next lectures. But for the rest of this lecture, we are going to talk about the importance of non-dimensional parameters, right? Non-dimensional parameters, we talked about Reynolds number, we talked about the Mach number, right? We will see Prandtl number. You have seen Prandtl number in your heat transfer, right? Yes? Okay. So, we are going to talk about some force and moment coefficients that are very important in aerodynamics and flight mechanics. Actually, they are important in structures as well because you are going to use them in your designs. So, let's talk about those. The first thing you want to talk about, let me actually start by saying this. Whatever kind of force you will have, you will get a force coefficient. So for lift, we are going to get a lift coefficient, C of L, right? For drag, we are going to get C of D, drag coefficient. For your axial force, we are going to get C of A, axial force coefficient. Normal force, C of N, normal force coefficient. For your moment, we are going to get moment coefficient. And we want to see how we can calculate these coefficients, or how did we define them? So because these are our definitions, right? We define this normalized coefficient. The first thing we do, the idea is to find these coefficients, we want to compare them to the dynamic pressure of the air that is flowing over your object. Okay? How can we calculate the dynamic pressure? Or who remembers what dynamic pressure was? Dynamic pressure. Okay, so how can you calculate? What's the equation for it? You're essentially going to bring down the air from full velocity, V infinity, to 0, right? That's it. So you are measuring the energy, total energy in a moving particle or moving air. What is the total energy in moving air? That's your kinetic energy, right? It is moving. You're bringing it down to a stop, to a full stop. Anyone? That's it. So dynamic pressure, you use Q infinity for it, which is 1/2 your density of air, the free stream density, V infinity squared. That's going to be your dynamic pressure. So we define any coefficient you want to deal with as the comparison of the force that it's related to with the dynamic pressure. So lift coefficient is going to be your lift divided by dynamic pressure. Let me actually use Q infinity here. Q infinity. Okay. So are we missing something here or no? This side has to be dimensionless. Is it dimensionless based on this definition or not? No, why not? Yeah, exactly. It's pressure, right? So newtons per meter square. So we have to multiply it by the area of your object. For a wing, it is going to be your span area. Let's say this is a top view of a wing. This is going to be the whole area of this wing is going to be is called a span area. So S. Lift coefficient, the same thing. LQ infinity S, and the same thing for the other coefficient. But when it comes to moment, it's going to be a little different, because in moment we have the contribution of the R, right? The moment R. So we are going to divide the moment by Q infinity to make it non-dimensional, multiplied by S, multiplied by a length. For the case of a wing, your length is going to be your mean chord. Again, this is a top view of the wing. I'm looking at the wing from the top, right? It's going to be your span area, and your chord length is going to be this. As you can see, it is changing, right? Just have to take the mean length of your chord, and you should be able to use it here. But if you are dealing with a sphere, your cross-sectional area would have been this S, yes. That's correct, sorry. I'm sorry, I don't see you. You are at the far end of the class, I don't see you. Yeah, so if you're dealing with a sphere, your area is going to be your cross-sectional area, and the length is going to be essentially the diameter for the CN, the diameter of the sphere, okay? Okay, so these are the main non-dimensional quantities that we are going to deal with in aerodynamics in general. In future chapters, your job is going to be to find CL and sometimes CD, but mostly we are going to focus on the lift coefficient. Lift coefficient is I don't want to say the most important thing in aerodynamic design and calculation, but it's usually the focus, right? You want to, like, if you want to compare two different wings to each other, you have to have the lift coefficient first and then the drag coefficient, right? And how it performs under different angles of attack. And the reasoning behind this non-dimensionalization is the reason behind all non-dimensionalizations. You can essentially, you want to be able to scale up, right? If I calculate the lift coefficient for a small airfoil in a wind tunnel, I can apply the same essentially result to a real wing that is operating under the same condition, like a big wing. Does that make sense? So, yeah. Okay. Is there any questions so far? No. That's good. It's either very good or very bad. I guess we're going to see. One thing that we have to mention is the other definitions we have for these coefficients. If you recall, we were dealing with the per unit span parameters. Like we were unit with lift per unit span, drag per unit span, or per unit length, if you will, right? I don't know, normal force per unit span, all of those things, right? But here we have lift, drag on the complete force, not just the per unit span force. So if you are dealing with a two-dimensional case, we are going to use a small c instead of a capital C, and then your per unit span force that you have calculated, Q infinity, this is newtons per meter, this is newtons per meters squared. So we are just going to multiply this by the chord length, or the average chord length if it's a wing. But it's a two-dimensional case, so we are only going to deal with the section of the wing or an airfoil. Does this make sense? The same principle applies to every one of these. So CD is going to become D prime, which is drag per unit span or per unit length, which is referring to the assumption we are making that the depth of the wing is 1 meters, right, in SI. Q infinity is C, and then for your moment coefficient, we are going to have M prime, Q infinity C squared, right? As this S becomes C, then C multiplied by C is going to be C squared. Any questions so far? Okay. So we have all of the equations that we need. We have the definitions of the force coefficients. We have the coefficient for the equation for moment per unit span. We have the equation for normal force, actual force. We have the relationship between lift and drag. So the next thing is going to essentially finding an equation for lift and drag coefficient as a function of pressure and shear, right? I'm not going to go through the details of it and how to get here, but that will be a bonus point for. Have we talked about bonus points at all? No, we will in a minute. So, well, let me just give you the equations, then we will go from there. So your normal force coefficient can be calculated, and this is per unit span again. The integral from 0 to C. 0 is the location at the leading edge. The trailing edge, your location is going to be the chord length, right? That's the maximum length you're going to see on the wing. Pressure coefficient on the lower surface minus the pressure coefficient on the upper surface, CPL minus CPU, dx plus integral of 0 to C, the friction coefficient on the upper surface, dy of the upper surface over dx of the upper surface, plus the friction coefficient of the lower surface, dy of the lower surface, dx of the lower surface. And then by dx. Okay. You have seen pressure coefficient and friction coefficient before, right? No? Yes, no? Yes. So how do we calculate pressure coefficient? Don't remember. That's all right. So let's go back to the definition here. The definition of whatever force coefficient or force per unit area coefficient we want to calculate, we have to divide that force or force per unit area, which is pressure, by the dynamic pressure. So based on this definition of force or force per unit area coefficients, what is the pressure coefficient? Think about it. We define the force coefficient as that force divided by Q infinity. What's the difference between force and pressure? Pressure is force per unit area. Essentially a force that is directed at one point, right? So based on the definition, what will be the pressure coefficient? Anyone? That's it. Pressure divided by Q. So that's going to be Cp. The only thing that I'm going to add to this is that we are going to deal with the pressure difference. So P minus free stream pressure divided by Q. What about the friction coefficient? Friction or shear force? Tau divided by Q. That's it. Okay? So we had in the equations, we previously had tau and P, but we have divided the equation by Q infinity to get the Cn. That's why you're going to see Cp and Cf instead of that. I'm going to write down the equation for Ca. Or actually, I'm going to give you that as a bonus point. Then I'm going to ask you to do a pop quiz. Don't know if you have enough time for a pop quiz, but so what is a bonus point? Bonus points in general, at the middle of the lecture, I may ask you to do something later at home, right? And you will get credit for it if you bring it back in a week, right? If you submit the answer to it for me. And the credit you're going to get for at the least amount of credit you are going to get for submitting a bonus point, one bonus point, is going to be 0.5% out of your final grade. Essentially, like homeworks are for undergrads are like 5%, so 0.5% for one bonus point, right? Does that make sense? And you can get up to 20% by submitting these bonus points. And these are not very hard questions, just plug and chug usually, right? So, get from n prime, the equation for n prime, to this equation. That's your bonus point. So essentially, you have to plug all that, the values divided by Q infinity, get to the equation, right? That's it. You essentially have to derive this equation using the previous information. Also, so that's 1/2 a point, right? Derive the equation for Cn. You are not going to get any derivations on your exam. So it's just that only derivations you're going to get are true bonus points. And another 0.5% is to find the normal force coefficient. Again, we are using the force per unit span definitions, okay, or force per unit length definition. And then the last thing is going to be the moment coefficient around the leading edge. So next week, you can get up to 1.5% of your final grade already without taking even one, without taking even one exam or submitting even one homework. Okay? And these are pretty easy. It shouldn't take you more than like, I don't know, an hour or two, right? Okay, is there any questions? No. So after you have found this, then we will go back to the original equations we had. Then we are going to divide it by Q infinity and find the relationship for CL between CL and Cn and Ca, which is Cn cosine of alpha minus Ca sine of alpha. CD, we are going to get Cn sine of alpha plus Ca cosine of alpha. Okay. Any questions so far? We have like 5 minutes, a little less than 5 minutes. I really wanted to do an attendance check or a pop quiz. I don't want to call it attendance check. It is a pop quiz, but I don't know if we have enough time. I guess we're gonna do it next week. So if you don't have any questions about anything, that's it for today's class. Again, I think I need to mention that the second half of the class we are going to do, by second half I mean it's going to be the fourth quarter of the class essentially. We are going to do flight mechanics instead of compressible fluid flow and viscous fluid flow, because we have two separate courses dedicated to those subjects. So I think we don't have any graduate level courses on or advanced undergrad on flight mechanics. So yeah, hopefully you'll enjoy the course and enjoy those topics. And that's it. Have a good night. Yes.
What was the unit on the C of what?
That's CF. That's the friction coefficient on the upper surface. CF and U. CF and U. Okay. Okay. How was the recording quality, guys? Online people. I guess I have to look into camera here. See, I have my GoPro. How was the recording quality, guys? Not great. Audio is great. Camera is a little fuzzy. Okay. Okay. We'll try to do better. Yellow chunk. Just give me 1 minute. It's hard to read sometimes. I'm gonna use the yellow chart more from next time. Definitely yellow. Okay. Just 1 minute. Okay, so yeah, have a good night, guys. I'm sorry, different sections of the class. I have to. Yeah, that's why I'm doing all this. I guess we have good technology.
So how do we